Okay, students, let us begin the class. Good afternoon, everyone.
Afternoon, sir.
In week 8, we will discuss about mainly root locus. Okay, we have discussed root locus several times as a preview, but starting today, we will discuss about the procedure in sketching a root locus and also discussing about the properties of root locus. Why we want to look at root locus is that because through root locus we can design a controller. Okay. One of the method in designing a control is using root locus instead. So far we haven't discussed about the methodology, right, to design a controller. We just do trial and error. Let us do PI, what happened. Let us do PID, what happened. But using root locus, we will be able to know whether this kind of controller will work or not. Reminder on the project. What happened so far? When is the due date?
Friday.
Isn't it 15 October? Tomorrow? Friday, not tomorrow. Tomorrow is the guest lecture, yeah. Guest lecture on senior colloquium, I forget. Yeah, apparently the person can come into our class tomorrow. So no, we are not using the Zoom tomorrow.
The project we have to also make the report for the design or
No need. I just want to see the thing and then it works.
so but the report don't need to include the design.
No need to write the report. I just want to see the model.
The checkpoint is it's done and it's working.
It's working. It's working means you can write down any codes and then let's say it rotates or okay.
Like the final
No need to write final report. No report. Just make the model. Okay. You don't have to write down any codes yet, but the condition is that you can write down the codes and then you can run the Arduino codes.
The codes are done per topic groups, right? Per small groups, right?
For this first step, it is for the 3 groups. Yeah,
The big groups.
the big groups. Yeah, no controller design yet. Okay. Other question for this? No. Let us do a week 7 materials review first. Yeah, before go into week 8. I want to discuss about this. Interesting, right? Since I think a lot of you are working together and maybe reaching the same answer. What is your first step in designing a controller? Okay, FPD. Let's say this is the drone. So what happened with the FPD? Okay, you have weight and then you have the thrust. Let's say the thrust is here. Thrust. And then after that, you write down. Okay. Is there anyone late? Atedio. Let's give him a surprise. Okay. Okay, let's say this is X lah. Mx double dot. So we have thrust minus mg. Okay, then what's next? Turn into Laplace transform. Then you have T of S minus, what do we call this? You can say WS, okay, that's fine. Okay, XS. So what happened after this one? Yeah, isolate XS, okay. So XS 1 over S square multiplied by, okay, then M. What didn't you say earlier? Okay. Ansel, no response from you? Same. So what's next? After you obtain what is XS, how do you make the block diagram? So this is the plan. What block? Okay, controller block. Let's say controller block is here. Then what is the signal coming here?
Yes, minus with W.
Huh?
Yes.
Here? You write down this?
No, I put another block.
What block?
W. Okay.
Another block here. You have a block here?
Yeah.
W?
Then minus. Yep.
Minus there, plus here. Actually, you don't need to write down the block, man, because the W is just a signal. Yeah. So this is just a signal of WS. Okay. Yeah, this is correct. Anyone different from this? What's the reason you put W here?
Because if you see at the formula, it represents the formula.
Okay. So we regard here the W as what? As a disturbance. Don't you say so to me this morning? There is no disturbance. Why? There is no disturbance here in terms of the drag force, no wind disturbance, yeah? But because we don't know what's the value of M, and so the weight is unknown, right? Weight is unknown, so this thing we can regard as a disturbance because it is a constant value. Okay. Then this goes your usual feedback loop. Okay, and let's say this is the H star, and this is the H of S. No, not H. We use X, yeah. Okay, so up to this point, you are good to go. Then how to design the controller? What controller you choose? What else? PI. Anyone choose different controller than PI controller? PD. One choose PI, one choose PD. Okay, let's say if it is PI, then your KS will be KP. If it is PD, will be KP plus KDS. Just this, right? So there is no extra zero, yeah, and there is no extra pole, only zero in here. Okay. So let us compare the two design. For PI, then let's see, I will have KPS over KI 1 over MS squared. Okay. Meanwhile, if it is the PD, you have KP plus, then you multiply with, yeah. Let's do the PI first. We have 3 zeros, 3 poles, yeah, at the origin. Is it at the origin? All of them? MS square equal to 0. So S can only be 0, yeah. So the 3 of them are here. Yeah, 3 of them are there.
Okay, that's not supposed to be different.
No, I'm talking about the root locus.
Oh, okay.
So the open loop poles are all here, yeah. Correct.
How many of the poles do
You count how many. What's the power of S in there?
3. Oh yeah.
3. So we have 3 open loop poles, and all of them are on the origin. How many open loop 0? One, which is at
negative AI over.
okay. So 3 open loop poles, and then 1 open loop 0. So that in that case we will have 3 minus 1 asymptote. So we have 2 asymptote. Okay. There will be a root locus in here. Okay. And another one will be, yeah, another one will be going there. Yeah, I think it will go there. So no matter what you do, your dominant pole will be unstable. PI control cannot work. Okay, PI control cannot. You want to try use MATLAB? Go into your MATLAB now. Go into the MATLAB. Yeah, you write down the numerator is KP and then KI. The numerator is, I believe this is M and then 0, 0, 0. Okay. Oh, it doesn't have. It's gone. Okay, and then your G will be TF, and then you write down root Locus G. You can. Okay, you check. I think the root locus will be like this. You put M at random lah. Let's say M is 10, KP 5, maybe KI is 1. Right. But what's the result? Are you there already? Let me see. Yeah, in the comment window. What's wrong on this one? Okay. Yeah, you can install also. Maybe for next week. KP you assume some KP like. Yeah, up to you. Yeah. No, there is no space. Huh? Oh, R locus, sorry, R locus. Sorry, R locus. Alhamdulillah, this is recorded ya. R locus. Yeah, you get it?
Yeah.
How is it? Huh? Okay. Yeah. Okay. Asymptote is 2, right? Sorry, I made a mistake. This is for, we have 3 asymptote. Okay, so the asymptote is one is 90 degree, the other one is 470 degree. So it turns out it goes like this. Okay. I mistyped the asymptote.
What is asymptote?
Asymptote is the direction where your closed loop pole will go if you increase the gain of your system. Okay, so you can see the closed loop pole, if you increase the gain, it will go here to the right. 2 of them will go to the right, and 1 of them will approach the open loop 0. Okay.
The asymptote number is the value of the highest one.
No, asymptote, number of asymptote is number of open loop poles minus zeros. Okay, we have 3 open loop poles and 1 open loop 0, right? So in this case, 2 asymptote. Yeah. Yeah. Well, the chair was there, so I just moved it there. So today is different. Okay, yeah, clearly PI control cannot work. Okay. Yeah, because of this. Yeah, the root locus says that the closed loop poles, the dominant one is on the right side of the imaginary axis, so it's unstable.
Also, ideally, you want the curves to be on the left.
The closed loop pole, you want it to be on the left. Yeah. If you find out the root locus to be like this, let's say, yeah, this is an example, yeah. Although it is impossible, let's say you root locus like this. Okay. Sorry. Go there. So you can choose this and that one. That's fine. But that's not the case, right? Okay. So now, without having to choose clearly what is KP and KI, we can estimate how our closed loop poles look like, right? And PI cannot work. Let us switch to PD. Okay. Now PD is more, you know, how many closed loop? No, open loop 0 is 1, yeah, and then open loop poles is 2, R2. So now we have the PD. 2 open loop poles in here, 0, and then 1 open loop 0 at the minus KP over KD. Okay, minus KP over KD. So there are 2 of them, and then 1 0, right? So we have 1 asymptote. 1 asymptote. If it is 1 asymptote, then it will go to the left. Okay. So the result is like this. 1 go here and 1 go there. Okay. Yeah. Yes, just like that. You are using smartphone?
Yeah, I randomly searched meta for mobile on Google and it.
Oh, okay. Okay. So PD can certainly work in this case, yeah, because it has stable closed loop. PID also can. Yeah, PD will work for the stability, but it cannot track the, it cannot track the X star because it has disturbance. Yeah. So PD also cannot answer the homework. Yeah. It can only answer the stability problem.
For homework, the correct answer is
PID. Yeah.
so. What does the circle mean?
The circle means This is the location of your closed loop poles.
Because the poles are valid and stable
If it is on the left of, yeah. In here is when you set your gain to be 0, yeah. It is here. Yeah, both of them 0. It is here. Open loop. The closed loop pole, when you set your K to be 0, is here. As you increase your K, they will go following this path. Okay, and when you are reaching here, some K are there when you have your system to be critically damped. Okay, you increase again your K, one closed loop pole go to the right, the other one go to the left. Then you can get your system to be over damped in here. Okay, if your system is here, then it is under damped. Yeah. Yeah, now we learn about the use of root locus. Yeah, at the expense of your homework. It's good to learn, right? You don't like learning? You hate it? Okay. Yeah, the final answer is not important at this moment, yeah, because you have limited resources, you have limited tools. But the most important thing is how you answer the problem, how you approach it. And up to this point, you did it good. Up to this point, yeah, you regard the unknown mass as a disturbance. Okay, unknown weight, I mean.
But there's no.
Huh?
Since we don't know the mass, it is a disturbance.
We assume it is as a disturbance. Yeah.
Why PD cannot satisfy
Your final value will not be extra.
if we only use PD?
Yeah, if you use only PD, then PD cannot eliminate the unknown weight completely. Cannot. Okay, the integral part can eliminate that, but PI only unstable. Yeah.
So every time there's a disturbance, it has to be high.
Yeah. If you want to track it, yeah. If you want to do perfect tracking, integral is needed. Okay, let's move on. I don't think I have to discuss this. This is easy, right? Easier than the first one because no one is asking about this. Okay. Another review is about the Rauf table. You make a table out from the polynomial that you want to test. Okay. And if you want to test the stability, then the polynomial that you take here is the characteristic equation. It's from the denominator, okay, where you will find the poles of the transfer function. And the last row of your Rauf table is always s to the power of 0. Yeah. And then you find out whether a system has, or a polynomial has, roots on the right half plane by checking the sign change. Okay. Then number of roots on the right half plane is equal to the number of sign change. So I'm not saying about the number of poles on the right half plane because we are talking about polynomial. Okay. As an example, if we have a system like this and we want to check the stability of the system, yeah, by checking what's the value of k, then we are interested with the denominator. Okay, so we take the denominator as the polynomial to test, make the Rauf table. Okay, follow the Rauf table convention, and then because this is the power of 1, so we only have 2 rows, okay, of the Rauf table. Sobri, any question? Not yet. Yeah, there is no computation to do in here because we only have 2 rows. Yeah, You only need to check is there any sign change or not. Is there any sign change here? Yeah, we don't know. Yeah, it depends on the value of k. So in this case, you have to find out what is the value of k so that the sign doesn't change. Yeah. Okay. I thought you want to ask a question. Yeah, it's between 0 and 5/3. Another exercise which I put on the lecture notes is this one. So this is a polynomial of the denominator, yeah, of the closed loop system. Okay, this one. We have 1, k minus 6, and then 5, and then k. Okay, and from here, what is the value of k so that the system remains stable?
For S1.
Yeah, in S1, so 4k minus 30 must be positive. Yeah, yeah, because k is positive, 5 positive, 1 positive, so we want to make this one also positive. So 4k must be greater than 30. Yeah, then k must be greater than 7.5. Yeah, if we sketch the root locus on that system, then we will have the open loop. The open loop will be k times s plus 1, s minus 1, s plus 6. Okay, let me erase this. This one no need, yeah, no need already. Now open loop poles 0 plus 1 minus 6, 0 plus 1, and then minus 6, and then open loop 0 minus 1. Yeah, in this case we will have open loop root locus here, and then another root locus here, and then we will have how many asymptotes? 3 minus 1, so 2 asymptotes. Okay, if it is 2 asymptotes, then the asymptote will be plus 90 and then 270. Yeah. For sure, the root locus that will go to the asymptote is root locus that coming from here. Yeah, they will go here and then they will break away and then goes to the asymptote. But I do not know where is the location of, where the asymptote cut down the real axis. Okay, so this asymptote could be here, could be there. Okay, could be somewhere. We have to compute them. Okay, and the closed loop system has the possibility to be stable if the asymptote is on the left side of the imaginary axis. Yeah, you get what I mean? There is a possibility for it to be stable if the asymptote is on the left side of the left imaginary axis. Yeah.
So, but there is the locus on the right side also.
Yeah, which is why, let's say the asymptote is here, yeah. Then what will happen is this. Okay.
So it's unstable.
Unstable for some k. After that, it is stable. Which is why you see k must be greater than 7.5. Okay, because from 0 to 7.5, it is unstable. Okay. Yeah. For marking the poles and zeros on the real axis on the complex plane, we use the open loop transfer function just to mark these points, but they are not the location of the closed loop poles. Okay. Okay. Now they are now connected. If, for example, the asymptote is here, yeah, there is no hope. Tak ada harapan ya. Go there, you see, just go home lah, just go home. Unstable, for eternity unstable. Okay, let's move on. Any question on that? No, Sobri? Yeah, only the first column.
Second one,
This one?
Yeah.
Only to help you to compute. This one only to help you to compute this, right?
Also, no meaning.
It has a meaning, but the sign changes. You only care for the first column. It has a meaning, of course.
Okay.
Yeah.
So we will have circle root locus. We only have one asymptote.
Circle root locus, one asymptote.
Yeah, why is this not circle?
We will discuss. Yeah. Okay, good question. Yeah, you are curious about that, which is why we have to learn about root locus now. Half point what? Oh, okay, now we start to discuss about root locus. From the Routh-Hurwitz criterion, yeah, RH is root, not root, yeah, Routh-Hurwitz. The Routh-Hurwitz criterion suggests that we cannot set k greater than 5 for 3, okay, because of closed loop instability. Because of this, yeah, sign changes happen. However, another question that I want to ask is that what is the fastest closed loop pole of this system? And then another question, can we design a controller to make the closed loop pole faster? Can you answer that?
Yes.
What's your basis of answering that? Okay, we will answer these two questions using root locus. Okay. Now first we define. Can sit here? Not nice. I cannot see the video. Let us define the root locus. Yeah. We will define the open loop transfer function to be G times H. Okay, you know where's the G, where's the H? Yeah, okay. Or you don't know where's the G and H? You know, yeah, the G is the one on the feedforward part, top part, and the H is on the bottom. Yeah. In most cases that we see, H is 1. So we call it unit feedback. But sometimes H is not 1. Sometimes. Okay, so on the top part, I write down the numerator as multiplication of S and then the 0, yeah. And then on the bottom, we take out the poles in there. Okay, so we have M0 and then N poles. I mean. So the root locus is the closed loop poles location when k is varied from 0 to infinity. Yeah, always from 0 to infinity. What's the root locus position? So in this case, from 0 to infinity. When k is varied from 0 to infinity, this is the location of the root locus. We have 3 closed loop poles, right? The first one is here. The second one is here. The third one is there. Okay? As we vary the k from 0 to infinity, that's what happens. The characteristic equation from the problem is this, yeah, 1 plus g h equal to 0. Yeah, that's the characteristic equation. The numerator of the closed loop, yes, the same. And so we can also say that root locus are all S satisfying this equation. Correct? Why? I'm just moving one to the right side. Okay. So we will draw the root locus by exploiting this relationship. You know how to exploit your friend? Yeah. So learn how to exploit an equation. Okay. Let us see. I want you to learn about plotting root locus using MATLAB. Can you plot root locus? This is wrong. Sorry. I have to amend it. R locus. Okay, can you do this? So just now we have a question, right? What is the fastest pole? The fastest closed loop poles of this system? And then, is there any possibility that we can design a controller to make the closed loop pole faster? Can you do using MATLAB? 1 minus 3 and then 1, 5.
That's how it was cool.
Okay, did you get this?
Yes.
Yeah. Okay, so based on this plot, what is the fastest pole? Minus 5, yeah. Minus 5. So minus 5 is when your k to be what? What's your k? If you want your closed loop pole to be 5, what is the k?
0.
K is 0. But k 0 is not possible, right?
Yes.
Yeah.
It will cancel the.
It will cancel everything, nothing happened, right? So if you want your system to be fast, your k must be relatively small. A bit weird, yeah? Small k makes your system fast. Big K make your system unstable. Okay? And this is exactly because you have open loop 0 on the right side. Yeah? you remember the system just now? S minus 3, S plus 5. This 0 is killing your system because it is on the right side. Okay? If you want your system to be faster, 0 must be on the left side of your pole. Okay? Bigger K, faster system. Makes a reasonable setting, right? Sorry?
What if the zeros are not
Oh, it's okay. You only have asymptote.
fully used?
Yeah, if it is no asymptote, then if there is no 0, then you just go to the left all the way. When you make K infinity, then your system is very, very, very fast.
That's technically better.
Yes, it is better. Okay. For this system, what is your recommendation on the controller if you want to have a faster pole? closed loop wall. What kind of controller that you will have in there? You try. If it is PD, what happened? If it is PID, what happened? You can try. Yeah. Check the open loop transfer function. Let me give you an idea, yeah, for the root locus. I will draw here, and this is the original system. Okay, -5, and then that is 3. If I add two poles, is it 2 poles and 1 0? Let's say I add two poles and 1 0, 2 open loop poles and 1 open loop 0 to this, and I will put them, let's say, sorry, this is too close. Okay, so, and I will have another one over here. Let's say this is my extra. Okay, let's say this is minus A, minus B, this is minus C. Okay, so if I do that, there will be poles over here, root locus here, I mean. Okay, and then another root locus will be here, and then another root locus over there. Wait. If I do that, am I the mistake? Wait. One asymptote. It is hindered here, yeah. Ah, okay. Yeah, so somehow I was thinking that if I can make this to go there, then I can push this somewhere on the left, more to the left. I can make the close loop pole to be faster. Just now the idea is gone. I don't know why. But the idea is gone. Yeah, yeah. Anyway, my idea just now is that because there will be root locus here. Yeah, I want the. Oh yeah, yeah, cannot. Sorry. This is wrong. I cannot do this. Most likely there is no hope for this system. I cannot make this one faster. This will just it will just die there. If I add another pole in here, root locus will stay here even closer to the. If there is a 0 over there, yeah. Let's try sometimes. Some other time lah, not now ya. Yeah.
So define the root locus from the poles to the zeros, or this is where it's at.
It is from the poles to the 0. Yeah, or from pole to the asymptote. Okay. Now another exercise that I want you to do is this. Can you use MATLAB to plot the root locus for this system? Yeah, the homework for next week is you plot root locus. Yeah. This was it. Okay.
Next week.
No.
Please.
You know how to do it already, right? Yeah, you don't have to put the k into the transfer function. S square 100. Anyone getting it? Do you get this figure? Yes. Anyone having problem? Yeah. So you see, you have two open loopholes here, yeah, from the 0, and then one open loop 0 in here. So it goes like that. Okay. Huh? Anyone still have problem on drawing the root locus? Yeah.
Can you show the one?
Jadi gini, kan kalau dikali satu kan ya udah satu aja apa yang cuma yang di GS-nya doang satu-satu doang. Oh iya.
Only this part.
Done.
Everyone done? Rafael done also. Ansel?
Dapat segini ini.
Yeah. Okay.
Dia tinggal lihat satu boleh satu.
Okay, the next one.
Ayo dia nih. Turunin dulu, Sir.
Okay, so this is the result.
Sir, turunin dulu, Sir. Bentar.
What?
Tanya aku melihat berapa ini.
Okay, that's the number.
Sir, what do you put in for the numerator?
One. One for the numerator. Which one? Oh, how to cross out? There is nothing to cross in there.
I think we obtained a different one.
Different?
Denominatornya 1, 2,3.
Ya.
Ya.
Ini kan? Yes.
Ya, ya.
1, 0,9, 2,03,
You mean this one?
5.
Ya.
Wow, okay. Yeah, this is the correct one, yeah. What happened in here?
Oh, 1.1.
There will be K for it to be unstable, yeah, over here, yeah, stable. Over here also, stable.
There you go.
Yeah.
So the system is always under them.
In this case, yeah, there are poles over here that are under them, yeah. Oh,
That means there are 4 asymptotes.
yeah, there are 4 asymptotes, correct. You see, if it is 4 asymptote, the angle will be 45 degree. Okay, this is 45 degree. 135. This is
So is it stable or not?
what? For some K, it is stable, yeah. K below, I think you can check the value of K here. Yeah, gain to 24.9. It is still stable. Starting 26 point something, that's unstable. Okay, you see the pole is already positive there. Yeah. Gain 26, it is still stable. Okay, next.
How to define the asymptote?
Later on, we will discuss. Yeah. Now we just do the MATLAB. Yeah. To make sure that you know how to plot using MATLAB. Yeah. There will be 4 asymptote also here, yeah.
Ya.
Okay. This is the answer ya, like this.
Oh.
Dari one.
All of you getting it?
Oke.
Okay, yeah. Also for asymptote. Yeah, just now I have an idea. I'm thinking. So I will put a new open loop 0 there, and then let me have another open loop pole over there. Okay. So in real axis, root locus will be here, and then another root locus there. Okay. But then there is no root locus here. No. Okay. Because we have two open loop pole and then two open loop 0, there is no asymptote. Okay. So that means this will go to here. Okay. What's good about this is that the root locus will go here, yeah, and all of them will break like that. I can push this more to the left, yeah, more to the left, so that this point will be far more to the left. So I will have k equal to something where the open loop pulse is much faster than -5. I can do that. Okay. Let's say I put 0 in here to be -2 and another pole to be, let's say, -10. Okay. So previously it is k s -3. My controller will be s plus 2, s plus 10. You try this. I just have my controller to be this one. I don't need to make a design. Is it PID or PI? Just based on the root locus. You can try this using MATLAB. Is it correct or not?
Itu kita expose itu ya.
Yeah. And then we have another s plus 2 and then s plus 10. So the system will be s minus 3, s plus 5, k s plus 2. Huh? Oh, there's no circle?
Oh, because the -5 is
It's plus 5, sir.
Huh?
-5.
Sorry?
S minus 3 over S plus 5.
Sorry. Plus 5, yeah. It is plus 5. Yeah, plus 5 there. The original system is plus 5. Yeah, you have a circle. So that means there is a K where your system is very fast over here, yeah. I hope you gain some understanding on how to use root locus. Okay. Okay, let's move on. What about this one? I think you can do it now. Now you can do it using MATLAB. And so because you can do it using MATLAB, now you can do it the homework. Okay, homework now you can do it. Wednesday you can submit. Let us discuss about properties then.
Okay.
Why it behaves like that, so we will discuss that now. The first thing is that it starts at the open loop poles. That means this is root locus when k equal to 0. When the k equal to 0, location of root locus is at open loop poles. And the root locus plot will end either open loop zeros and asymptote. If we have asymptote, in this case we don't have asymptote, so all of the root locus will end at the 0. So 0 is like a sink. It's a sink, also like a black hole. All of them is sucked in. And then the number of asymptote is equal to the number of open loop poles minus open loop 0. Which is why when they are the same number, we don't have asymptote. What if the number of 0 is greater than the number of pole? Cannot, the system is not proper.
Because mechanism works and the root locus will always
It will go to the circle. No, not always a circle. Not always a circle. An example is like this. No asymptote. It will just be here. Another example is, let's say you have it here and another 0 over there. So it will go here and then I don't know, maybe going there. I don't know. I don't know. It can also go up directly, but there is no asymptote in this case. It will be from poles to 0, but there will be some root locus on the real axis. For sure.
What if it's
What?
3 open loop poles?
Also the same. But I can do this. Like that. To the left. Here again and then here again. Okay. So easy to catch. The next property is that root locus location on the real axis. It will be on the left of the odd number open loop pole and 0. What does it mean? So I'm taking this example. We have 4 combined open loop 0 and open loop poles. I will number them. This is number 1, this is number 2, number 3, number 4. So the rule says it will be on the left of the odd number. On the left of number 1, the real axis. On the real axis. We don't have anything on the left of number 2. We don't have, but we have on the left of number 3. Do we have anything on the left of number 4? No, it is even number. That's the location on the real axis. Understand? Yes, that's right. Hey. Any question on this?
Say the poles is in like number 1 and number 2, right? But if number 1 is poles, number 2 is
they will be the same.
still the same.
So it doesn't matter whether this is pole or zeros. The important thing is the number.
We always number it
From the right side.
Number of poles.
No, we are not doing subtraction in here. We don't. Which one? Which one that you are asking? Oh, number of asymptotes. Yeah, number of poles. In here we have two. We have two poles. We are not doing -5, -10. Yeah, we don't do that. But we have two open loop poles, and then two open loop 0. Okay. Yeah, that is used to find out number of asymptote. It has no asymptote, correct? Okay. Next, on this example, let us discuss on this example. Do we have open loop poles?
Yes.
What's the open loop pole here? Huh? -5. Okay. Open loop 0, do we have? +3. Any asymptote? No. Correct. Numbering the open loop poles and 0 on the real axis. That's what we do, yeah. Mark location of root locus on real axis. Okay, so especially for that problem, I will just draw again for completeness. Okay, 3 and then -5. Number out the pole and 0. Yeah, on the left of the odd number, so it's here. That's it.
Ya.
So what's the difference if I have like this? This is 3 -5. What happened? Where's the root locus? The same, yeah. Same location is here, yeah.
Let's say we have odd amount of poles and zeros.
Odd amount.
Of poles and zeros. So 1, 2, 3. That means the locus in between of 1, 2, and then 3 to infinity.
Yes.
Ya.
Yeah.
Yeah. 2, 3 di sini kan.
Yeah.
3 ke kiri.
But it is impossible to have 2, 0, 1 pole. No.
2 poles, 1, 0.
Yeah, 2 poles, 1, 0 is possible. So like this, then you will have that. This is number 1, 2, this is number 3. Okay, yeah. To 0, 1 pole is impossible. Okay, what else I have to discuss? Any question on this? No. Okay, one more example, and then we finish today. Yeah. On this example, what is 3? Open loop poles. Okay.
3
Plus 3. Yes, we have 1. And then the angle of asymptote.
So asymptote go from here to here, then to the real axis.
Yeah. Okay. So to find out the angle of asymptote, this angle is measured from the positive real axis. Okay. Positive real axis. Where is positive real axis?
Quadrant 1. Yeah, quadrant 1.
Real axis. I'm not saying quadrant 1. No. So the k is from 0, 1 to 3, etc. If
Okay, sir.
k is just an index. Different. That's capital K, yeah. Capital K. Big K. This is small k.
How you define small k?
If asymptote is just 1, you use k to be 0.
Oh,
Oh, berarti K is number of asymptote minus 1.
No. Okay. You use k to be 0, yeah. If you only need to find one asymptote. One asymptote, right? You use k to be 0. If you have two asymptote, k to be 0, and then the next one, k to be 1. Okay. If it is 3 asymptote,
0, 1, 2.
yeah, 0, 1, 2. Ah, smart.
So k is n minus 1. So in probably 3, 7, 5.
Yeah, correct.
So we have 3 different angles.
Yes, if 3 asymptote, yeah.
That's right.
This one only 1 asymptote, okay?
Okay.
Yeah, 1 asymptote. Example is that one. Let's say this is the minus 9, yeah. If it is minus 9, so asymptote that one, yeah. And so numbering open loop poles on and 0 on the real axis, and then we mark the location. We mark it already, yeah. Okay, one more example lah. This one, because the asymptote now, how many asymptote you think?
What?
2.
2.
Yeah. Open loop poles
0 and no.
0 and minus 1. Okay. Steven,
Are you okay, Stephen?
what's the open loop 0? Hah? Ah, correct. Wah, okay ya. Mantap, Steven. Naturally aspirated. No. Not available. Who said naturally aspirated? Who said that? Naturally aspirated. Okay, any asymptote? We have 2, yeah? How do we know 2?
2 minus 0.
2 minus 0.
180.
Okay, you use k to be 0 and 1, yeah, to find out the angle of asymptote. Okay. And then we number open loop poles and 0 on the real axis. Okay. If we have asymptote to be, if the asymptote is other than 180, then you have to find out intersection of asymptote with real axis. Yeah, okay.
When the asymptote intersects
The real axis. Yes.
Jadi lokasi asymptote di mana?
Yes.
Okay, let us draw ya.
Lagi pada 3.
0 and then minus 1. After that, we have the asymptote plus minus 90, 170. Okay, like this, yeah, like that. But we don't know where. So let's say if it is here, yeah, then this point is the intersection of asymptote with real axis. But we can compute that. How to compute that? Do the math, of course, yeah. We do this. Sigma A is the intersection of asymptote with real axis. You do that by sum of 0, and then you divide by poles minus number of 0. Yeah. You just do the math on the 0 minus 1, then we get minus half. Okay. So that means this point over here is minus half.
So no matter how many the angle is,
There is only one. Yes, correct.
Sum of all is
Sum of all, you have 0 and then minus 1, right? 0 plus minus 1. So you have minus 1 on the top. Okay. Huh? This one? Huh? Sigma A is the intersection between the asymptote and the real axis. It's just a notation. It is just a notation. Yeah. Yeah. Okay. Correct. Yeah.
Shallow. Is that supposed to be -1 -0?
-1 -0?
I know, I guess.
No. We have 0 and then plus -1
Yeah, and then
minus nothing.
Yeah.
Minus nothing.
So I thought you said that negative PI is 0.
Yeah.
No, no, no.
Sigma PI is 0.
Sigma PI 0, sigma CI.
No, no, no. There is no 0, yeah. Okay. All right. Now this is just an intersection, yeah. But we know that on the real axis, these are our root locus, yeah. The next question is that how does the root locus go into the asymptote? Where does these two root locus break or depart? Yeah. Let's say if it is from here, yeah, the departure point is from here. Then what will happen is that we'll go here, go like that. Okay. If this is the location of where they break away. Okay. So we need to find out what is the location of breakaway.
How?
Yeah, how to do it? Do the math again.
Do the math again.
Now, another math to do is you compute the breakaway point. I'm saying here that they will surely leave the real axis. They will, right? They have to approach asymptote. But where they will depart, you need to compute. To do this, yeah, this is a bit confusing in here. You see, you express the characteristic equation first, yeah, and then after that you express a function of k. K is something. K is a function of s. After that, you take the derivative of the equation with respect to s. You take the derivative, yeah, with respect to s. Okay, and after that, this will be your s. Coincidentally, the s is -½ also the same with the intersection point. Just go straight up. Okay. So this thing is not happening, yeah. It will just go up like that.
How do you know if it will go down? For example, from X, go up or go down?
Yeah, one of them will go up, one of them will go down.
Yeah,
Of course. No, you just draw that.
Oh, from calculation.
No, you are just drawing this, yeah. You are not doing this going to down, this going up. We are not counting the direction. No, we just do this.
We just know when it is.
Yeah. Okay. These are the same pole. Okay. Because the conjugate, they are the same pair. Okay. Complex number cannot live without its conjugate. Cannot stay. So they are actually the same pole. So we will end the class here. We will resume again with another example, yeah, on Wednesday. Okay.